In this tutorial, I'm going to discuss some of the issues using real models. Uh, we've been using simple transmission lines in some of the other tutorials. I'm going to use a microstrip line. Most of the libraries that Mason has that are a little bit more advanced, like the microstrip, the strip line, the coplanar, you can find a microstrip properties value. Now the properties is really another variable block that defines the permittivity, the dielectric height, the loss tangent, the sealing height for metal above the microstrip line. Different parameters that aren't going to change much or ever for your microstrip line. And you can see that these arguments inside of the microstrip line, we have these plugged in. Now if you wanted to, you could hard code instead of having EPSR, this 3.48 defined as a variable. You could just modify this to be 4, 6, whatever. So we have some width and some length. Those are the only parameters that are going to commonly vary for this microstrip line. And of course we can have units on those. And so this is what I call a dynamic component. The values are generated algebraically but on the fly, so you could pretty much have any width or length value as long as you don't break certain assumptions. Now I'm also going to pull up a touchstone model. This is a static model. So in here we actually link to files that are located in our Mason model library. You can get to this folder if you go into your start menu under Circuit Mason. There's a link to here. And so in addition to having like the microstrip lines, we also have some resistor touchstone files that we get from the vendor. So we have 38 different models that are in here, going up to 1,000 ohms in this particular model. And what I'm going to look for is my closest model to 50 ohms. I have this 47 ohm model. Now I'm limited because I can't just pick any resistance value, but this does have all the parasitics. So I'm going to take this 47 ohm resistor, which was number 22, and you can optimize using the genetic optimizer and the simplex optimizer over the different values of resistor. You can do that while you're also doing the continuous primitive component, dynamic component simulation. So I'm going to generate my symbol references, and I'm going to run Mason now. So if I put up a plot, I see that I have a pretty good match across here. By default, I tend to have 50 ohm structures by default, but what I'd really like to do is calculate what the exact width is for 50 ohms, and while I'm at it, I'm going to figure out what the length is for 90 degrees. So I'm going to pull up PrimCalc. You can get to PrimCalc through the Start menu like you do for Circuit Mason, and what I can do here is I can actually calculate, given microstrip line structure. So this is the Mason model library. I can go to my M-line structure. I know it's M-line because it tells me where the model is that defines this. And I can plug in different values. 30 mils, we'll make a 3 centimeter line and calculate that. And it'll tell me what the impedance, the electrical length is, the loss in dB per meters, but I can also synthesize a transmission line by clicking on and telling it what variables I want to allow to be flexible in the argument list and which ones I want to be fixed. So if I calculate this, it's going to throw in the reverse, and it's going to tell me what the width and the length is in the units that I previously defined. So let me go back and put in my 20.6 mils and 4.5 0.5 centimeters, and run Mason again, and I should see my performance get marginally better as I moved from being probably like a 48 ohm line to a 50 ohm line.